In the previous class, the Schrodinger wave equation for hydrogen-like atom is obtained. It is very similar to particle in three-dimensional ball. We can use the same equation except mass is replaced by reduced mass of electron and nucleus. In this, the Laplacian operator is converted into spherical polar coordinates. It is given in Clark's table. So there is no need to memorize, or you can also memorize. The derivation is a little bit tedious. Further, the Schrodinger wave equation in spherical polar coordinates can be readily separated into three independent equations, as follows. We have shown already, by using separation of variables. These are the three independent equations obtained from the Schrodinger wave equation. Each equation depends only on one variable. For example, equation 1 depends only on radius vector. The equation 2 depends only on theta. Similarly, equation 3 depends only on phi. The equations 2 and 3 are similar to rigid rotator theta phi equation. So, if you have studied the rigid rotator problem, you have studied half of the hydrogen atom problem. Okay.
Good morning. Let us study today part 2 quantum theory of hydrogen-like atom. In the previous class, we have derived the Schrodinger wave equation for hydrogen-like atom from particle in three-dimensional box. The Schrodinger wave equation of hydrogen-like atom is very similar to particle in three-dimensional box. The Laplacian operator in the Schrodinger wave equation is converted into spherical polar coordinates del square. The del square value in spherical polar coordinates is given in Clark's table. So you can easily convert the Cartesian coordinate, Schrodinger wave equation in Cartesian coordinate into spherical polar coordinates. It can be readily solved, the Schrodinger wave equation in spherical polar coordinates can be readily solved to give three independent equations. Each depends on only one variable. Remember, each depends on only one variable. Let us see first the third equation, phi equation in reverse order, because this is the simplest second order differential equation and it can be readily solved by using differentiation rules. The solutions are, the wave functions are phi equal to a e power I m phi. This is the unnormalized wave function. Please remember, this is the unnormalized wave function. This wave function is normalized by using normalization condition. I was shown in the last few slides. The normalized wave function is where a is a proportionality constant or integration constant. By using normalization condition, the value of a is obtained. A equal to 1 by square root of 2 pi. This is called a normalization constant. This is called a normalization constant and this is called a normalized wave function. Now, where m is a constant. What is the value of m now? How it is determined? It was asked in CSIR gate question. Any wave function, if it is well behaved, it must have a single value. For single valued wave function phi equal to phi plus 2 pi because of spherical symmetry. Phi value varies in the range of 0 to 2 pi. Okay, it is spherically symmetric. Therefore, C equal to C plus 2 pi. Therefore, A e power I m p equal to, then you substitute here and it can be written, it can be split into two terms, and therefore this is, you can strike this one, therefore E I m 2 pi equal to 1. ML can have values 0, plus or minus 1, plus or minus 2, plus or minus 3. These are the values which can satisfy this equation to give value 1. Okay. By mathematically, these are the values. For example, m equal to 0, then e power 0 equal to 1. Similarly, plus 1. If you put 1 here, you will get the whole expression equal to 1 minus 1. Okay, these are the values, eigen values. These are the eigen values which satisfy this equation. But ML is called magnetic quantum number. ML is called a magnetic quantum number, thus we have obtained a quantum number. Okay. Similarly, the second equation, the theta and phi equations and the solutions are similar to rigid rotator problem. We have already solved the phi equation, theta equation. They are very similar to rigid rotator problem. Therefore, by solving the equation 2, the theta wave function is obtained as follows. Theta is the function of theta n Lm p L modulus m cos theta. The theta wave function, the wave function is expressed in the form of associated Legendre polynomial. Okay, so it consists of the wave function is solved by using Legendre polynomial. The L is called orbital or spherical quantum number. By solving this equation, the value of beta is obtained, L into L plus 1. Beta is another constant. Okay, these L equal to 0, 1, 2. These are the values satisfies this equation. Okay, let us now see the first equation, the radial equation. The solutions are rather complicated for radial wave equation. However, it is obtained mathematically as follows. The radial wave RR equal to n L e power minus rho by 2 rho power L. This is called Laguerre polynomial. So the radial wave function can be solved by using Laguerre polynomial, associated Laguerre polynomial. This constant n L is called a normalization constant, where rho equal to 2z by n a naught r, and n is called the principal quantum number. N is called the principal quantum number. Okay, so we have obtained the magnetic quantum number. There are 3 quantum numbers obtained by solving the Schrodinger wave equation. This was asked in GATE examination. How many quantum numbers are obtained by solving the Schrodinger wave equation? Therefore, there are 3 quantum numbers obtained by solving the spin quantum number is not obtained from quantum theory, or it is obtained. It is a obtained from classical analog. Okay. So when n equal to, when n is an integer called 1, 2, 3 principal quantum number. Similarly, by solving this radial equation 1, the energy expression is obtained as follows. This energy expression is same as Bohr energy equation, Bohr energy level equation. Both were given awarded Nobel Prize for obtaining the electronic spectra of hydrogen. Both agree with each other. Okay, and the mu is the reduced mass of electron and nucleus, and Z is the nuclear charge, H is Planck's constant. The negative value in the energy expression represents or signifies that electron is bound to the nucleus, because electron is bound to the nucleus by electrostatic force of attraction. It has negative sign, and A naught equal to Bohr first radius. We have already studied in Bohr theory 4 pi epsilon naught h cross square divided by mu e square, where E is the electronic charge, not exponential. H cross equal to h by 2 pi. So we have obtained the on solving the Schrodinger wave equation of hydrogen atom, we have obtained the energy levels and also the wave functions and quantum numbers. The total wave function is the product of, here we have already seen the radial wave function and angular wave functions. We have now obtained, you can substitute RR, the radial wave function here, and theta wave function here, and phi wave function here. Okay, where RR is the radial wave function and theta phi are called angular wave function or spherical polynomials. The radial wave function obtained from this for substituting n equal to 1, n equal to 0, n equal to 0 in this expression. The radial wave function is obtained as follows: R1 is equal to 2 into z by a naught to the power 3 by 2. Normalization constant, this is normalization constant, e power minus zr by a naught, that is n1s. This will be useful for solving many problems, which we will see. Several problems were asked based on this radial wave function. Thank you for watching.